Welcome back everyone to this lecture on running PyTorch for GPU. Before starting this lecture, make sure you've created another environment that has that CUDA version of PyTorch for the correct version of CUDA that has been installed with your NVIDIA card. Or make sure that you're actually using one of the cloud services discussed in the previous lecture. So if you're having any issues with that installation process discussed in the previous lecture, please refer to those official links in the previous lecture that we've linked to as supplemental resources for the most up-to-date information. This particular lecture is instead going to focus on how to actually run the PyTorch code on GPU with CUDA. And you'll see that there's really just a few minor things we need to tweak in our code in order to run it on the GPU. With that being said, let's go ahead and open up a notebook and get started. Okay, here I am at a fresh notebook. First thing I want to do is to make sure that I'm actually using CUDA with Torch. So after importing Torch, in order to actually check if CUDA is available, we say torch.CUDA and then is available. It's a method call off of this. And after running that, you should see true. If you're seeing false, it means you're still running Torch on the CPU and you need to go back and check out the resource links in the previous lecture. Okay. So now that we understand that we're actually using CUDA, let's go ahead and check out how to use CUDA and GPU and then confirm not just that we're using CUDA, but what device we're using. So one way to do this is the GPU device on the hardware is going to have an ID. In order to get that ID, we type torch.CUDA and then go ahead and select current device. You can just tab autocomplete this. It's a method call and it will essentially give you the ID, and most likely it's going to be 0. In order to actually get the name and see what basically what hardware you're running this on, is to say torch.CUDA, and then we'll say get device name, and then we'll pass in that ID, which was just given to us from the previous one. And then you'll see that on my particular computer, I'm using GeForce GTX 1080 Ti. So this is my graphics card. And yours will most likely be different depending on what actual hardware you're using. Okay, what we can also do is check how much memory I've actually allocated on my GPU. Because if we're running a really large notebook and maybe we have multiple models, what's going to happen is PyTorch will end up taking more and more memory off of your GPU. So it's going to end up using more and more of it. So often with really large notebooks that maybe you have a couple models in without realizing it, you may actually end up running out of space on your GPU. So a really nice check for that is to just ask for torch.CUDA, and then there's memory allocated. Open and close parentheses, go ahead and run that. And right now it says 0 for me because I haven't really used anything yet. This is a fresh notebook, I don't have anything else running. But this returns the current GPU memory usage by tensors, and the unit here is in bytes. So this is for the given device. Okay, so what we can also do here is we can check the current GPU memory managed by the caching allocator in bytes for a given device. And we do that by simply saying torch.CUDA, and similarly it's memory cached. And in this case, and if you're following along, it should be 0 for both since we haven't really done anything yet. Okay, so now let's focus on what changes do we have to actually make in order to use CUDA instead of our CPU. Now, typically for a CPU, what we would do is we would define torch tensors. And we could do this simply by saying A is equal to some floating tensor. And for instance, I'm going to make a very simple one, such as 1.0 and then 2.0. So there's just two numbers in this tensor, and I haven't done anything yet. I run A, I see the tensor here, but if I check the particular device that this tensor is being stored on, it's actually by default being stored on my CPU. So step number 1, in order to use CUDA and GPU instead of CPU, what we need to do is actually specify that we're using the GPU when we're creating our tensors. So step 1 is whenever you're creating a tensor is to make sure you call CUDA off of it. So what I will do here is write the exact same code, float tensor, again really simple tensor here, but after this I'm going to call CUDA as an additional method call. So now that I run that, notice it takes a little bit longer because it's first accessing that GPU and then writing it there. And now if I check the device that this tensor is stored on, it'll say type CUDA. So just by default, even if you're running on GPU and CUDA is available, the tensors by default will go onto your CPU. You need to remember that whenever you're creating these tensors, at the very end, you call .CUDA. So that's one change you need to do. And we can then also check out how much memory is being allocated. So I can copy and paste this command. And we now see there's 512 bytes being allocated from CUDA because now this float tensor is on CUDA on my GPU. But that's change number one that we have to do. Essentially, whenever you call tensor, remember to call .CUDA off of it. And then the second change you have to do is simply send the actual model to the GPU. So I'm going to create a model and essentially just send it to the GPU. And we'll see that's actually quite easy to do. I'm going to copy and paste our basic imports as we've done before. I don't need to re-import Torch, so I'll go ahead and take that off. But NN, functional dataset data loader, essentially, this is all the sort of imports we did in one of the very first sections of the course on basic artificial neural networks. And now what I'm going to do is I'm going to copy and paste the same model we used in the very beginnings of the course when we were dealing with just fully connected ANN models. So here I can see my first model. It's just two fully connected layers here. We have some sort of number of hidden layers, etc. Notice none of this code is different than what we've done in the past. So now what I need to do is create the model. So I will create a manual seed, just as we've always done. Go ahead and choose some arbitrary number, and then create an instance of the model. Okay, so far we have the model, but what we need to do is let's check if this model, again, is on the CPU or GPU. One way I can do that is by taking advantage of calling the parameters off the model. And parameters is essentially a generator. So there's a built-in keyword in Python called the next that allows me to essentially iterate through a generator. And what I'm going to do is then for each of those parameters, I can say is CUDA, which is an attribute. And there's a link in the actual lecture notebook where there's a discussion on how to check if the model itself is on CUDA. We previously just showed you how to check if a tensor is on CUDA or CPU. This is going to be able to check if the model parameters are on the GPU. So if you run this right now, it will say false. So currently, our model is actually not on the GPU. So how do we actually change this? Well, luckily, it's pretty simple. All we need to do is say GPU model is equal to the model we just created, except dot CUDA, essentially sending it to now the GPU. This is pretty much the exact same thing we just did with the tensors. With the tensors, to go from the default CPU to CUDA and GPU, we simply called .CUDA, open and close parentheses, after creating that tensor. We'll end up doing the same thing with the model. After creating the model, what we can do is say .CUDA, and that sends it to the GPU. And now I can rerun this. I can say next, except this time instead of typing model, I'll say GPU model, ask for those parameters, and then check is CUDA, run that, and now it's true. So now our model is actually in the GPU. So finally, let's go ahead and take a look at the iris dataset that we did in the very beginning of the course and see how this is all affected by changing things to the GPU. And the main things you have to consider is whenever you create a tensor, and this goes for any project that we've done so far, either RNNs or CNNs, basically, whenever you're creating that tensor and you want it to run on GPU, step number one is check that CUDA is available. Step number two is for all these tensors, call .CUDA on them. And then step number three is to simply make sure your model is sent to the GPU, again, with a .CUDA call. It's essentially just make sure that your tensors and models are called with .CUDA at the end of them. So let's again take a look at the iris dataset. So essentially going to repeat one of the very first problems we saw, except this time we're going to do it with a GPU model. So underneath my data folder, I'm going to ask again for that iris dataset. So we'll go ahead and read that in. I'll set my features equal to df drop the target along axis equal to 1 because it's a column. And then I just want to grab those values as numpy. So if I take a look at x, it's that array. We've seen this before. Now let's go ahead and grab the targets, which is just going to be y is equal to df target dot values. So here right now I'm reading from a CSV file, and now I've read this in, grabbed my features, grab my target values. What I need to do is now do a train test split. We can do that easily with scikit-learn. I already imported train test split here. So we'll pass an x, y. Go ahead and choose a test size. I'll choose 20% for my test size. And then to make sure we get the same split, you can go ahead and say a random state of 33. And here, what's a nice little trick is you just say Shift-Tab on train test split, expand on this, and if you scroll all the way down, it gives you a little bit of code that you can just copy and paste in order to get that variable split. So this essentially splits it into 4 pieces: the train and test features, and the train and test labels. So far I haven't done anything with CUDA. What I need to do is now convert these NumPy arrays into tensors. So how do we do this again? We simply say xtrain is equal to torch.float tensor, and we will pass in our NumPy data. Now this is what we did previously before in the rest of the lectures. Now the only thing I need to add to make sure that it's running on the GPU is, just as I mentioned, simply add .CUDA to it, and it's as simple as that. And I can copy and paste from our notebook, and I repeat this for the test set as well as the training set for both features and labels. Essentially the exact same process we did before, but wherever you happen to call or create a tensor, make sure you add .CUDA to the end of it. So we run that, and now we have not just PyTorch tensors, but PyTorch tensors running on my GPU. Now recall back in the artificial neural network section, when we were dealing with a really large data set, such as that New York City taxi data set, we created a data loader object to handle all of it. For the iris data set, because it's much smaller, we didn't need to do that. But there is a small tweak you need to do to your data loader object if you do intend to use it for a GPU. So I'm going to copy and paste what the data loaders would look like for a CPU. So typically for a CPU, what you would do is you would say train loader, data loader, xtrain, set your batch size, and then for the training set, we set shuffle to true. For the test set, we set shuffle to false. Now, if you're running this on GPU, what you want to do is you want to add in one line here called pin underscore memory is equal to true. And if we take a look at this, as well as the documentation for data loader, essentially expand it, what we're doing here is the default is to pin memory equal to false. And if we scroll down here and see what it actually does, if we set pin memory to true, the data loader will copy tensors into CUDA pin memory before returning them. So that helps speed up the training if you have CUDA available on your GPU. So that's the one thing we want to make sure we add here if you end up deciding to use a data loader. For really small things, such as the iris dataset, we don't use data loader, but for larger datasets, such as that New York City taxi dataset, we did end up using data loader. So I'll go ahead and run this, but we won't end up using it for this smaller dataset, but I do want to make it clear when you're working with datasets such as the New York City dataset, then you're going to want to make sure you set pin memory underscore or pin underscore memory equal to true for both of these. Okay, so then what's next? Essentially, we're just going to set our criterion and optimizer. For this, there's no changes necessary, so I'll copy and paste these just as we did before. We've seen these a bunch of times, and we're lucky since for GPU usage, we don't need to change anything here. So we'll go ahead and run that. And finally, let's go ahead and train everything on this GPU. We'll go ahead and import time, and this will allow us to see just how much faster training is depending on your GPU you're using. So we'll set a start time, and then the end time will be time.time minus start. And we'll go ahead and print how long this took. I'll use some f-string literal formatting here. So use total time, and we'll go ahead and print out end. And let's go ahead and do the training. So for the training, I'm just going to use these raw tensors here. I won't worry about the data loader, but you can always reference our artificial neural network sections for code on how to use the data loader. We use that for the New York City taxi dataset. And I will say for I, in range of epochs, let's go ahead and train this for 100 epochs. And we'll set a list to keep track of our losses. So for I in range epochs, let's get a little space here. What I'm going to do is we'll say my Y predicted value is simply getting my, GPU model, and then calling forward on xtrain. So that's my predicted value. I need to figure out how far off I am. So I compare the loss here using criterion, between what is y predicted versus what's the correct y train. And then we'll say losses, append the loss. Okay, so then let's go ahead and just print out our progress. So we'll say if I mod 10 is equal to 0, go ahead and print out the epoch we're on. So we'll say epoch I, and we'll print out the loss we're on. So that'll be loss item. And then the last thing we're going to do here is, after we went ahead and printed out that epoch and that loss in line with the if, we'll take our optimizer, and just as always we say, whoops, make sure we spell this right, optimizer, then say 0 grad or 0 gradient, go ahead and perform back propagation, loss.backward, and then optimizer step. Okay, we'll go ahead and run this. And we'll see that even for 100 epochs, the training time is almost nothing. It's basically less than half a second, so very, very fast. Much faster than what it was when we ran this on CPU. And then I'm going to just copy and paste from the notes. We've actually seen this before, but it's testing on the test set. So what we do here is, this is essentially a lot of print formatting, but we've already seen this. Keep track of how many we got correct. Then torch with no gradient updates, so basically just running this on the test set. Go ahead and grab X test, and then check GPU model forward on that particular data point. We get our predicted Y value. Then we go ahead and compare whether our predicted Y value was correct or not, and then we'll go ahead and print out these results. So we run this. We can see right here, notice now everything dictates that it's on the CUDA device. We get our predictions out, as well as the raw tensor that came out of this, and we see here that in this particular case, for this random split, we got 100% correct. Okay, great. So what do we need to know in order to run things on GPU? There's 3 main changes. Change number 1 is whenever you create a tensor, make sure you're calling .CUDA method after it. Change number 2 is to go ahead and make sure you're calling .CUDA off creating your model. Then change number 3 is, if you happen to be using data loader, go ahead and make sure you say pin_memory is equal to true. All you need to do is remember to do those 3 changes to your code, and pretty much everything else stays the same, as long as you just remember to, wherever you reference the model, reference your GPU model, such as GPU model.parameters or GPU model.forward, etc. Okay, thanks, and I'll see you at the next lecture.